Today, we're talking about our newest research paper, which deals with the coherent control of an atomic scale spin qubit on a surface. Hi there, my name is Andreas Heinrich, and I'm the director of the Center for Quantum Nanoscience here at Eba Women's University in Seoul, South Korea.
Hello everyone, I am Soo-hyon Phark. I am working as a scientist at the Center for Quantum Nanoscience.
So this current paper is about the coherent control of a single qubit. Now, what does that mean? So a qubit is the basic element of quantum information science. So a system that we can control typically with two levels. And what we show in this paper in particular is that we can do the full control of a single qubit. When we compare a classical bit and a quantum bit, you will see that the quantum bit is much more complex and has much more potential for using its information. What does that mean? So a classical bit is always either in state 0 or in state 1, and it never does anything more complicated than that. But a quantum bit can be in superposition states where you are in between state 0 and state 1, and so in order to know which is the exact state of a single quantum bit, qubit, we have to perform more operations than in a classical bit. And for example, we need to know, if we think of the qubit as a vector, it's pointing in a certain spatial direction, we want to know both the x, y, and the z component of this vector to fully quantify what is the state of this qubit. So to fully control a single quantum bit, let's think about this as a vector that is on a ball. We call that ball the Bloch sphere. It's a very typical name that you hear in quantum information science. And the qubit points along a certain vector in that sphere. So it has an arrow starting from the center of the sphere and points towards the outside of the sphere. And what we have done so far, before this paper, we rotated the vector in a certain plane. So we could go between pointing north pole to pointing south pole and back to the north pole. What we show in this paper, that in addition to do this, we can also go in the other directions. If you think about this on the Earth, on the globe, right? If you want to go from the North Pole to the South Pole, you have many ways to go, right? And for example, if you are on the equator, you are in between the North Pole and the South Pole, but you still want to be able to be somewhere else on this equator and to coherently control where you are on this equator. In order to do this, we need to have very fine control of the microwaves that we use to manipulate these qubits. And so from a purely technical point of view, here we demonstrate this kind of advanced microwave control of a single atom qubit on a surface.
So basically, using ESR technique, or so-called pulsed ESR techniques, that we can rotate the qubit vectors from north pole to the south pole of the Bloch sphere. So if we apply some radio frequency voltages to our STM junctions, then it actually plays the role of the driving force of the spin resonance, and it can rotate the direction of the spin qubit.
So you may ask yourself the question, so what's special about using atoms or molecules on surfaces, right, for this quantum information science? And I think there's a really powerful answer to that kind of question, and that is that you have the tunability that we need here. So we can put one of these qubits a certain distance from another qubit, and we can change this qubit from, say, the same atom. In this case, we use titanium atoms on magnesium oxide thin films. We can change this one to a molecule or to a different type of atoms. And so we have a lot of flexibility in building structures with atomic scale precision. And this really makes our qubit platform very different from other material systems where you are kind of stuck in using a particular material, like a particular superconductor or a particular NV center in diamond, for example. It's difficult to change this to another material. And here we have a lot of flexibility because we have our qubits available on the surface of our material. So if we look back a little bit in time, so about 2015, so 8 years ago, we were able for the first time to do so-called electron spin resonance on a single atom on a surface. This is really the precursor to doing this coherent manipulation when we can call this single spin a quantum bit, a qubit. In 2019, we followed this up with the control of the qubit on this Bloch sphere in one direction, right? And then there was a natural step to look at other qubits in other implementations, such as superconducting devices, for example, to know that in order to really have full control of a qubit, we need to do all directions, not just one direction. And so conceptually, the step was relatively straightforward, but the devil, as always, is in the detail. And here to implement this kind of advanced microwave control for single atoms, that's really the technical achievement that we did here.
Okay, as you can see here in the first A and B figures, then the A actually shows the basic scheme of the operation of qubit, and in B you can see how it can be applied to the STM junction. So so-called electron spin resonance in STM, we can drive and measure the qubit state. And here at the bottom side of the B, then you can see two different colored RF signal switches applied to our STM junctions. And the first one basically is used in C to rotate our vector about x-axis. And the second blue guy basically subsequently are used to rotate our vector about y-axis. So this kind of technique is so-called two-axis control of the qubit vector. Of course, we were really happy at the moment we first see this is working, because we actually made a plan to do this for the first time using STM. And then usually in the research field, nobody knows what actually could happen in the future or next few days. Who knows that? So the scientific research always have a low probability of success in terms of the planning. But we actually planned this properly and got the result quite quickly than we expected. So we actually make ourselves quite confident that now we are starting to really control the qubits using STM. Of course, we did. And the celebration, the best celebration is at the time, real time, when we got the data, always. Of course, we can go to the pub or some kind of nice place to celebrate and drunken. But there's always the post-time celebration. The real-time celebration was really exciting, and nobody actually can control their mind or their emotional states when they see the first data. So we celebrated really a lot overnight. So we are 8 in total, and 5 members basically belongs to the Center for Quantum Nanoscience, and 3 guys basically outside the QNS, and 2 guys basically stayed here for some while and collaborate and contributed to the work.
It's always a challenge in our line of work that the time scale to do an experiment is kind of measured in months or sometimes even years, and rather than days or weeks. And this makes this field a little bit challenging, of course, because you cannot publish 10 papers from one system. Maybe if you're lucky, you get 2 or 3 papers per year, right? And so in this particular case, the time was on the order of 6 months. So there is a very obvious next step that we have to take and that we are already taking, which is to go from a single qubit to multiple qubits, right? If we want to do quantum information science, for example, entanglement measurements, then we need to have at least 2 qubits. And so the really difficult challenge that we are advancing on now is to use the scanning tunneling microscope, which allows us to work with individual atoms and molecules on surfaces, to not only control a single qubit, as demonstrated in this paper, but to simultaneously, at the same time, control 2, 3, and so on, more qubits, then we can really implement quantum information algorithms in these atomic scale systems.